Greetings everyone. We are going to finish up Module 11 with a discussion of lenses in which we explore how the phenomenon of refraction can be exploited to create image formation. But just as a little review about the law of refraction, or Snell's law, we had discussed in the previous lecture how we can quantify how much refraction to expect based on this equation here, that the index of refraction of the medium that you're coming from times the sine of the incident angle should equal the index of refraction of the material you are being refracted into times the sine of the refracted angle. And we discussed how these indices of refraction are related to the speed with which light can travel through that particular medium. That is, that this is a ratio of the speed of light divided by the speed of light in a vacuum divided by the speed that light can travel through the medium. So what we concluded was that if you're going from a medium in which light can travel relatively quickly into a medium that comparatively light has to slow down in, then you will see that the refracted ray will be bending towards the normal. And then the reverse will be true. If you're going from a medium in which light has to be traveling fairly slow and then going into a medium where light can travel comparatively faster, then you expect to see, based on the law of refraction, that the refracted ray will be bending away from the normal. So based on that little review, or recap, you can look at the drawings below and determine which of these has to be an incorrect depiction of what happens. If you would like to pause the video while you look them over, feel free. I'm just going to go on and discuss what the correct answer is here. So the important pieces of information we need to know in order to answer this conceptual question, or what are these indices of refraction of the various substances. So glass, the index of refraction, if you recall from the chart that we talked about in the last lecture, is approximately 1.5, and water is going to be equal to approximately 1.3. Air is going to be equal to approximately 1. Okay, and those are the three substances that we are dealing with. The higher the index of refraction, the slower the light travels in that substance. So when we are going from, say, glass into water, if I am going from an index of refraction that is relatively high to an index of refraction that is lower, then I expect there to be a refraction away from the normal. That is not actually happening here, right? This angle is larger than this angle. So this is one that could be incorrect. So let's take a look at the others and see what we have. So going from air into water, we are going from a lower index of refraction to a higher index of refraction. So we expect to see bending towards the normal. That is to say that the refracted angle is going to be larger than the incident angle, and we do see smaller than the incident angle, and we do see that that's the case. So the incident angle is larger than the refracted angle, that is, that it's refracted in such a way that this ray is bending towards the normal, so this is okay. And if we go from air into glass, that's going to be a similar situation. Air is the quote-unquote quickest of all of these media, so anything that's going from air to either water or glass should be bending towards the normal, and indeed we see that that's happening here. And then if we're going from water, with an index of refraction of 1.3 to glass of 1.5, then we should expect to see bending towards the normal because we are going from an index of refraction that is lower to one that is higher, right? So we expect this light to have to slow down more in the glass and for the ray to be then refracted more and bend towards the normal. And indeed, that's the case. Okay, so all of these check out except for A. That would be the correct answer to this particular question. Okay, so hopefully you're able to reason through things like that. Of course, you also want to be able to utilize this equation here and quantify exactly how much the refracted angle is and or what the index of refraction is and so on, like we did in the example that we discussed last time. Okay, so now we're going to apply this idea of refraction to image formation through the use of lenses. There are different shapes of lenses. All of these different shapes have some kind of given focal length, and the reciprocal of that focal length is what we're going to call power. Later on, we're going to see how this relates to the diopter of your corrective lenses if you have some sort of glasses that require your eyesight to be corrected. We're going to do that later in the lecture, but for now, let's just discuss the different kinds of lenses and how the refraction works through these different lenses. So broadly speaking, there are two categories that we're going to consider: converging lenses and diverging lenses. And within those categories, there are various shapes that we can have. We're going to constrain our discussion primarily to the biconvex and the biconcave shape, as those are the easiest to understand. So whenever you're trying to determine how an image forms through refraction through a lens, you're going to draw a ray tracing diagram similar to how you would draw this with a mirror, as we discussed in Module 10. So we're going to draw three rays again. And just like with the mirror, we looked at, the tangent line where the ray hits the surface of the mirror, and then we looked at how that would result in reflection and what direction that would go in. And you can do the same thing here with the idea of refraction and think about how the light would be refracted at the tangent to the surface here at this interface, and then how it would be refracted again as it is leaving the lens. So rather than bouncing back off, we're trying to figure out how to draw these rays and refract them through the lens. So the rule of thumb that you can use is your first ray that you're going to draw in your ray tracing diagram will just go parallel to this axis, the same way that we did principal axis, same way we did with a mirror. Okay, and then when it's refracted out of the lens, if it's a converging lens, which is convex or biconvex, then it will go straight through the focus on the other side. And then the second ray we're going to draw through the focus on the left-hand side of the convex converging lens, and what that will result in is a ray that is parallel to the principal axis after it exits the lens. And then the third ray hits the lens in just such a way that the refraction as it enters and leaves ends up making the ray continue on its original path, and you can see that all three of these rays in your ray tracing diagram converge on a single point. Since they came from the tip of the arrow of the object, then that corresponds to the tip of the arrow for the image. And just as we did with mirrors, then we're able to conclude that sometimes this results in an upside down or inverted image, as is the case here. And the ratio of the height of one to the other will tell you something about the magnification of that image. Okay, so in this converging lens situation with this ray tracing diagram, what I end up with is a real image. In other words, I could stick a projector there and it could project the object's image onto the screen, and the image is also inverted. Okay, so what happens if I have a diverging lens? This is a lot more complicated, but we can also use ray tracing to help us here. For a diverging lens, the ray that goes in parallel is going to diverge, right? All of these rays will somehow diverge from where they were originally pointed, right? And we can draw the three rays and we see that they're not going to converge on a single point on the other side. However, if I create a dotted line to see where they appear to originate from, if they had just been going straight, then I see that all three rays converge on a point on the same side of the lens as the object. And so that's going to correspond to the tip of the arrow in this example, and this leaves us with an upright image. It's not inverted this time. But it's also not a real image. It is smaller and it is what we would call a virtual image. Okay, so we can generalize these things into different cases. If you have a converging lens and you stick your object outside of the focal length, you will end up with this real inverted image. But if you stick the object inside the focus, then you can also end up with a virtual image, much like you would with a diverging lens, but this virtual image is going to be to the left of the object and it's going to be magnified, whereas with the diverging lens it will be to the right of the object and it will be smaller. Okay, so qualitatively speaking, conceptually speaking, those are the cases to bear in mind when you're dealing with lenses and image formation by lenses. We want to quantify this, of course, though, but the nice thing is that the thin lens equation, as we call it, is really basically mathematically identical to the mirror equation, which we already discussed in Module 10. And like the mirror equation, there are going to be a set of sign conventions that you'll need to follow. Most of these should be sensible to you if you draw analogies to what the sign conventions were for a mirror. But effectively, we're going to assign a plus or a minus to the focal length depending on if it's a converging or a diverging lens. And then we're going to typically always have the object to the left of the lens. So, almost always this distance to the object is going to be positive. But then whether the image is real or virtual will determine whether we get a plus sign or a minus sign for that. And then the magnification equation is also identical to what we had with a mirror. Note the minus sign here. So in order to end up with a positive value, you also need a minus sign for the image. That is to say, it's got to be virtual. Otherwise, you will have a minus sign in your magnification, and then that will tell you that this thing is inverted. The numerical value of the magnification will then also tell you whether the object is enlarged or smaller than usual. Magnifications of greater than 1 will be something that is enlarged. Magnifications less than 1 will be something that is smaller than the actual object's size. Okay, so why don't we take all of these points and let's apply them to an example of a converging lens. So in this example, we have some sort of a converging lens that has a focal length which was given to us. Okay, and the focal length here is going to be equal to 15 centimeters. And because this is a converging lens, this will be a positive sign. You can go back to the sign conventions to verify that for a converging lens, we need a positive sign for the focal length. Okay, and then we're going to place the object at actually a pretty great distance here in this example, so that this distance here, the distance to the object, it could be an arrow or whatever you like it to be, DO is going to be equal to your 50 centimeters. Now, just like I pointed out when we were using the mirror equation, there's no need to convert this to meters per se, as long as we keep all of the units the same. So if we're working in centimeters, we can keep all those centimeters as long as we understand then that our answer will also be in centimeters. There are various questions being asked in this example. We want to know what type of image is formed. If you see this type of image, we mean, is it real or is it virtual? Okay, and we want to know where it will be located. That is to say, we want to know what is DI. Okay, so the real and virtual can come out in my sign conventions. If I go back here, remember that if in the end I get a positive sign for my image distance, it will be a real image. If I get a negative sign for my image distance, it will be a virtual image. So therefore, I can just apply this thin lens equation and see whether DI is positive or negative. I can also reason through this by going back yet another slide and realizing that I have a converging lens with an object placed outside the focal length. So I'm going to expect what will come out of this will be a real image rather than a virtual image. Okay, so let's see if that prediction holds true. We're going to take the thin lens equation, 1 over f equal to 1 over di plus 1 over do, and we're going to plug in the values that we see. If you do this, then you should, well, let's solve actually for di. So this implies that 1 over di is going to be equal to 1 over f minus 1 over do. And in this case, both f and do are positive, but once you plug in the numbers, you should see that you end up with a positive value. This 1 over the image distance is going to be equal to a positive 0.05, roughly speaking, and the units here then would be centimeters to the minus 1 because this is just 1 over the image distance. So if I then invert this and take 1 over that value, I should find that my image distance, there are actually a few more digits here that I've just rounded. So if you don't round until the end, what you should find is that the image distance is 21.4 centimeters. And since this is greater than 0, then this implies that we have a real image. Okay, so it does fit with our prediction based on the ray tracing diagram. All right, so we're going to move on and we're going to discuss a natural type of lens, that is the human eye. So the eye you see here belongs to my daughter, my firstborn, and when this picture was taken, her eye perfectly focused through the lens of her eye, an image on the back of her eye or the retina of her eye, and she could clearly see what it was she was attempting to focus on. Since that time, she now wears corrective lenses so that that point of focus is no longer hitting the retina of her eye without the corrective lenses. And we're going to talk about how that kind of refraction and image formation through corrective lenses takes place in some examples. So for a normal eye that has what we would call 20/20 vision, what happens is that when light enters the lens, it is refracted perfectly so that the image forms right on the retina of the eye and then can send a signal to your brain that interprets what it is that you're seeing. Notice that that image is actually upside down. So one of the things your brain has to do is invert that and take that information and turn it right side up. For someone who is nearsighted, that is to say they have myopia, they can only see things near to them clearly. What happens is that when the light goes through their lens, it does not hit the retina, it falls short of the retina. The focus is somewhere inside the eye, not at the back of the eye where the retina should be. For someone who is far-sighted, that is that they only see well further away but not necessarily as well closer, then the focus is actually overshooting and it should form in the back of their eye rather than on the retina. So the reasons for the image forming at these maladaptive locations tends to be the shape of the eye and or the shape of the lens over time has been somewhat distorted, and so for someone with myopia, their eye and or lens is either elongated, typically elongated, so that the focus is not quite reaching the back of their eye. Whereas someone with hyperopia or farsightedness, their lens and or eye is foreshortened, and so it's overshooting and placing the focus beyond the bounds of where the back of their eye should be. So we can actually quantify what a corrective lens needs to do based on the thin lens equation. So here's your thin lens equation here, and it turns out that as long as I keep this in meters rather than centimeters, here's where the unit actually matters, then this will be the familiar diopter that 1 over the focal length will be the diopter that you would use for your eyeglasses or other corrective lenses. So, they don't tend to mention this, but say, for example, you have a -2, they just say it without a unit. If you are curious what the units of your diopter actually are, the units of the diopter then are 1 over meters. Okay, so why don't we take an example of someone who requires corrective lenses for myopia. I'll just use myself as an example here, and we will determine just how bad my eyesight really is. So the diopter of my glasses or contact lenses in 1 over meters is going to be equal to 1 over the distance to the image plus 1 over the distance to the object. Now that's a little fuzzy. What do we mean by the distance to the object? Ideally speaking, if I want to correct the vision appropriately, we want to be able to focus out to infinity, quote unquote. In other words, we want the image distance to be equal to infinity. And 1 over infinity is equal to 0. So actually this equation simplifies quite a lot because we are going to put 1 over infinity here, which is just going to turn into 0. So my diopter should be 1 over the distance to the image. What do we mean by the distance to the image? This is how close do I need to put the object in order to be able to see it without my corrective lens. Okay, so in order to solve for this, let me tell you that my diopter is pretty bad. It's about -5. One eye is slightly less than that, but we'll just use -5 for simplicity. Okay, so if I want to see how close I need the object to be in order to be able to see it, this is where an image will be able to form clearly for me without my glasses. Then I can take 1 over this, and I will see that the image distance that I can see is 0.2 meters, which is approximately 7.9 inches. And you can test this at home with your diopter if you want. I actually did this just as an experiment. But if I take my glasses off and I place the image or place the object about 8 inches from my face, then lo and behold, I can focus on it and see it pretty clearly. But if I move it further away than 8 inches from my eye, then it becomes quite fuzzy quite quickly. Okay, so let's take a look at the other example. Let's say that instead of being nearsighted, you're actually farsighted. This is a little bit more complex of a concept to explain, because we talk about near points and far points. So in this case, the near point, what we mean by the near point is this is the nearest that you can see clearly. So if I bring stuff closer to my face than this, then it will become out of focus. Okay, and so we're going to treat that like our image distance. Okay, and we're going to try to make the object look like it's further away at that near point. Okay, the object is where it is, right? I can't change that. This is my DO. But this is going to be my DI because I want to create the illusion that the object is actually at that location instead so that I can focus on it. Okay, remember that we're going to be creating a real image in this case, so we need some sort of converging lens, and we want to produce this illusion that it's further away than it actually is so that I can focus on it. Okay, so let's take an example. Let's say we want to know what power or diopter we need if the near point, which I'll abbreviate as NP, is equal to 1.02 meters, and let's make it a little bit trickier this time. We'll say this is the distance from the eye. Okay, the reason this will be trickier is because our glasses don't necessarily sit directly on our eye. So we're going to take the glasses distance to be 2 centimeters from the eye. Okay, and we want to be able to focus on something that is 20 centimeters away. We want to be able to at least correct to that point. Okay, so based on the equation that we had on the previous slide, we want 1 over the DO plus 1 over the DI. Okay, and we are going to assign 20 centimeters to the object distance, and to the image distance, we're going to subtract that 2 centimeters off so that we end up with just 1 meter, and we are then subtracting this from here because of our sign conventions. So we have 0.2 meters for the object distance minus 1 over 1 meter for the image distance. What this gives me then is a plus 4 for my diopter. So this could be a little bit of a challenge to find in the drugstore if you're just trying to find reading glasses. You may need to actually visit an optometrist if you need a diopter that large. It's worth noting that in this era, corrective lenses are not the only option to correct one's vision. Another example of corrective vision is the laser vision correction, which has become more and more affordable as time goes on. And what happens here is that your cornea is essentially reshaped, and that allows the focus to be placed on the back of your retina instead of falling short, where in a case where you have myopia. Okay, so that basically wraps up our Module 11. The next thing we will be discussing is Module 12, and I wish you a good weekend.